Okay, so thank you very much for letting me speak here. So let me first wish a very good, very happy birthday to Gilbert and to Martin. Before I start, I will do a little bit of history. The history starts in Toulouse, where I was a PhD student with Gilbert as an advisor. And someday I had to fill a form, and I remember this form. There was something special about it. And so I did some serious archaeological investigations. And I did manage to find this form. Here it is. So it's a form for something. I mean, nobody cares about. I mean, it's a form, and there are random informations, and there was a point I couldn't fill in. So okay, my name, I was a PhD student and everything. This I could fill, and then name of my PhD advisor, but then somehow it asked about the PhD of the advisor. So I went to Gilbert and asked, well. Okay, well, could you please fill in this line? And he said, well, don't put anything. I mean, if they ask, I will answer. Okay. Okay, so there are two things I learned with this form. That first thing that maybe I didn't learn it right away, but Gilbert didn't have a PhD and doesn't have a PhD. And second thing is that you don't really care about what's on the form, usually. I mean, it's... Okay. Still, I mean, I wonder, I was worried that there was some kind of scam somewhere or something. But I knew I was in good hands with Gilbert, and there was another... little story. It was summer, it was hot, and I was having, it was in Toulouse, and I was having a picnic with my wife on the grass in front of the building. So that's not exactly the exact place, but, and the nice thing to have when you have a picnic there is watermelon. Watermelon is nice, it's refreshing and everything. And the point that you need a knife to cut it, and you have to be able to use a knife. And something happened, and okay, I did cut my finger, maybe not as badly as this, but fortunately there were not so many people around. Fortunately, Gilbert was around, and and was able to carry me to the hospital, which was not far. Okay, so I knew I was in good hands. All right, so more mathematical stuff. So what I want to talk about is some class of natural subgroups of AutoFN. And more generally, you would consider, instead of the free group Fn, some hyperbolic group, or probably torsion-free hyperbolic group to make statements simpler, or sometimes to make the statement true. Thorough, relatively hyperbolic groups, etc. So I will, maybe, all the statements I will give will be in this kind of context. And what do I mean by natural subgroups? What are those natural subgroups? Well, the first kind of subgroups you may think of is the group of automorphisms that fix a given subset or a given subgroup, meaning pointwise. So all automorphisms that restrict to the identity on a given subgroup H. Okay? That's a natural subgroup of, say, out of a group of automorphism here. It's rather, okay, I will be maybe fuzzy in the distinction between out and ought, like in my, like in the way of saying it probably. A second kind of subgroup you can consider is the group of automorphisms that preserve globally a given subgroup. So it's larger. You just ask that the automorphism sends H globally to H. Okay? That's a larger subgroup, more complicated. Something important in all this is you're given a splitting of G, say a decomposition into a free product or an amalgamatic free product, or by Basser theory, it's the same thing as an action on some simplicial tree. And you're looking at all automorphisms that preserves this splitting. The definition is that there should be an isometry from the Basser tree to itself that encodes the automorphism in the sense that it's alpha equivariant. So maybe I should, alpha equivariant means, it commutes with the action of G up to the automorphism of alpha. Another equivalent way of putting it is saying that it preserves, the automorphism preserves the length function. So for any element G, its translation length in T is the same as the translation length of its image under the automorphism. Okay, so that's another natural subgroup, the subgroup of automorphism preserving a splitting. There is you can generalize this last one to a more general setting when, well, you want to understand the subgroup of automorphism that preserve some R-tree, some action on an R-tree. So the definition is exactly the same, but this time you don't have an action on a simplicial tree, but an action on an R-tree. And general question is, okay, understand all those groups. Okay. So the plan here of my talk is to start with the description of the stabilizer of the splitting. This will be just algebraic, essentially, and that would be the motivation for an introduction of McCool groups. McCool groups are not neither 1, 2, 3, or 4. But it's essentially, it's very close to automorphism fixing the subgroup, but you have several subgroups, and so we'll see that later. And so they are very important in all I'm going to say. Then, so that will serve as an introduction to McCool groups, and then I will state some results about the other kinds of natural subgroups here, and then explain how the method we use to study these groups, and mention the results that came around this study. All right, so let's first start with the stabilizer of a splitting. So you have a splitting, so I decided to choose an example so here it's a graph of group with 3 vertex groups, A1, A2, A3, and 2 edge groups, E1, E2. And G is the fundamental group of this graph of groups, and that gives, by Basser theory, an action on a tree. And here I'm assuming that the edge groups are finite or virtually cyclic, because that's the most important case. And you can view such a graph of group decomposition as the graph of spaces. So one space x1 whose fundamental group is A1, one space x2 whose fundamental group is A2, one space x3 whose fundamental group is A3, and 2 edge spaces, red and blue, whose fundamental groups are E1 and E2, probably cyclic on the picture, and which encode the amalgamation. All right, so the fundamental group of this graph of spaces here is the group G. Now, if an automorphism preserves the splitting, then it will permute the vertex groups. So up to finite index, going to a finite index subgroups, you can assume that there's no permutation induced, and you really get a morphism. When you restrict your automorphism to A1, you get a morphism from, say, A1 to A1, which is not exactly true. You have to use a conjugation to ensure this, and so you get really a map to the outer automorphism group. And so to each automorphism alpha, okay, preserving the splitting, if it does not permute the three factors, then you get three automorphisms, outer automorphism, one of A1, one of A2, and one of A3. Okay, so you get this map. This 0 here means that you go to a finite index subgroup, and you get this map from a finite index subgroup of the stabilizer of this group to the product of the three groups. Now, this map is not onto, because there are constraints on the automorphisms alpha A. Okay, so what are the constraints? The obvious constraints is that, for instance, the automorphism you see on A2 should preserve the conjugacy class of E1 and E2. Now, E1 and E2, I assume that they were finite or cyclic, or virtually cyclic, I didn't remember. Then, in this case, what's happening is that the induced automorphism of this group is has finite order. So here again, up to going to a further finite index subgroup, you can assume that your automorphism is actually the identity, or it fixes the subgroups E1 and E2 up to conjugacy. And that's not, I mean, I should be more precise with this fixed up to conjugacy, and that so that will be the definition of a McCool group. Here is first a topological interpretation. Maybe it's better to look at what's going on in the middle vertex, so in X2. And the topological interpretation of this fixes E1, E2 up to conjugacy is the fact that you can represent your automorphism by a map that is the identity, I mean fixes pointwise the blue and the red stuff. Okay, it fixes the edge spaces. Okay, and that's the topological picture you should have in mind in the definition of a McCool group. So McCool group is an algebraic definition, and which is not so easy to understand. And the topological the picture is easier. You take all homeomorphisms that are the identity on some subspaces, but because of problems of base points, there are inner automorphisms that come here. Oops. So the definition of a McCool group, so you're given a group G and several subgroups H1, Hk. So here, the group G would be, say, A2, and the subgroup H1, Hk would be the two H groups. Then the McCool group corresponding to this data is the group of automorphisms that act trivially on each subgroup here in the following sense. The restriction to each Hi is inner. Okay, and the inner depends on the index, on the inner list. Okay, so that's a definition of a McCool group, and essentially what I explain is that the automorphisms alpha 1, alpha 2, alpha 3 you get, they lie in this McCool group. Maybe an example to make this more concrete. This is a surface group with boundary. Its fundamental group is a free group of rank 5, I guess. And if you now look at A and B, the two boundary components, they define a cyclic group. And the McCool group corresponding to that, so this data is exactly the mapping class group of the surface that's drawn here. Okay, so it's a subgroup of out of F5 that is that corresponds to the mapping class group of this surface. So the theorem by Gilbert Levitt and the following work by Bass and Jiang says that you can fully understand the stabilizer of the tree in terms of these McCool groups. It says that the stabilizer of the tree has a finite index subgroup that fits in an exact sequence. It maps onto the direct product of those McCool groups, the McCool groups of the vertex groups, and you ask that it acts as the identity or trivially on the incident edge groups. And the kernel of this map is virtually a group of twists on which I won't say much. In this picture, you should think about den twist around these tubes. Okay. All right. So that's about what I wanted to say about the stabilizer of a simple short twist. There's no geometry here. It's really algebra or topology. There's no hyperbolicity involved in particular. So there's no. This works in very generality. There's no hypothesis on the group. I know. Okay. So now, if you want to, to generalize such a theorem to R trees, then we have been able to prove something in this direction. So if you take an R tree that lies in the boundary of outer space, so it's an action of the free group on this R tree, and you want to understand its stabilizer. Well, the theorem is that you can understand it in terms of McCool groups. So there is a finite index subgroup of the stabilizer, and it fits in an exact sequence. On the right, it's a direct product of McCool groups. Okay, McCool groups of subgroups of Fn. It's not McCool groups of Fn. It's McCool groups of some subgroups. These subgroups are related with the treaty, and they are vertex stabilizers. This part here is a product of free groups. Okay, so for instance, if you know that McCool groups are finitely presented, you get that the stabilizer of the tree is finitely presented. And if you know more finiteness properties for this one, you will get more finiteness properties for this one. Okay. So that's a first result I wanted to mention about natural subgroups. There's another one. So it's not really a theorem, it's a wish. So we would like to understand the stabilizer of a subgroup, the global stabilizer. So that was the second kind of natural subgroups. And well, we don't know. Okay, we hope that someday we'll be able to understand, but right now we don't. And so there's you can view this question in a dual way. So you may want to understand the automorphisms of H that extend to the free group, and understand this group. So the best result maybe, I mean, the easiest to state, the result easiest to state is the following. It's when the subgroup is malnormal, because then you can state it this way. If the subgroup of the free group is malnormal, then the group of automorphisms of H that extend to the free group is virtually a McCool group of H. Okay. So, so all those results.
Was there a motivation behind the original question?
Well, I'm lost. This one? Yeah. I don't know any deep motivation for this one. I mean, yeah, just a natural subgroup. Yeah. So in all those results, you see that McCool groups were involved. Okay. So here, stabilizer of an R3 was described in terms of McCool groups. The stabilizer of this malnormal subgroup is described in terms of McCool groups. So it would be good if you can say something about McCool groups, and you can. So first, McCool groups have been studied by McCool. It doesn't seem to be, the general, feature for names. But okay, so they have been studied by McCool for the free group and for cyclic subgroups. But in fact, they happen to be the same as McCool groups of, the McCool groups as I define them. And so the theorem says that in terms of finiteness properties, McCool groups behave very nicely. So if you are in a total relatively hyperbolic group, so torsion-free hyperbolic groups, for instance. Oh, I didn't say what it is. A total relatively hyperbolic groups are torsion-free relatively hyperbolic group whose parabolic subgroups are free abelian. Okay. Yes, in particular, torsion-free hyperbolic groups are of this kind, and so McCool proved finite presentations of those groups in Fn. Cohen-Volkmann proved the finite classifying space for virtual subgroups. Yes, also in the free group. For one-handed hyperbolic groups, this follows from result by Sella. And so we did this result with Gilbert. Well, we should say that even in a fixed group F4, there are infinitely many such McCool groups, not only up to conjugacy, but even up to isomorphism. So it's a large class of subgroups, and interesting. And we proved this result about a chain condition. So when you have McCool groups, they could be nested with respect to each other. But what we proved is that there is a bound on the length of a chain of such McCool groups. So if you take a McCool group, an inclusion of McCool groups of the group G here, then there is a bound on a chain like this. This is something that we needed for to understand the stabilizers of R3s. Okay. And another result here, another finiteness result, says that in a McCool group of G, there are only finitely many conjugacy classes of finite subgroups. Okay. So let me just talk about consequences of this. Let me call it FCF property. I don't have a good name. So finite. There are finitely many conjugacy classes of finite subgroups. Okay. So this has nice corollaries. So for instance, if you take such a relatively hyperbolic group. So here, in fact, it works in a slightly more general setting. I mean, you may allow torsion and you may allow polycyclic parabolic groups. But if you fix such a group, then there are only finitely many isomorphism classes of groups G prime that contain G with index bounded by some number K. Okay. Now here's maybe a warning. So if you take L, the lamplighter group, you take infinitely many copies of Z over 2. You take the direct product and you make Z act on them by shifting. This is a lamplighter group. It's a solvable group, and you take this free product with Z over 2Z. Okay. Well, this group has infinitely many index 2 supergroups up to isomorphism. Okay, and this is a relatively hyperbolic group. This is a group which is hyperbolic relative to these solvable groups here. So, okay, so so it's not true for every group, you know, that there are just there are groups where this kind of statement doesn't hold, and even relatively hyperbolic groups. Here's another version of the corollary, which says that here you have no bound on the index. If there's no bound on the index, but you assume that the important here, the important assumption is that G is normal in the larger group, then there are only finitely many possible G prime. You have to assume, say, torsion-free to avoid, you know, taking a direct product with a finite group, for instance. Okay. Why are these corollaries of the fact that there are only finitely many conjugacy classes of finite subgroups? Well, because there is a theory for classification of extensions of groups. So if you have a group G prime that fits in an extension, so it's a finite index supergroup. So this one is normal in this one, say. And then, so the quotient is a finite group. So this F here is a finite group. This is your original G, and this is a G prime. And theory of extensions tells you that G prime is determined by two things. The first thing is the cohomology of this finite group F with coefficient in the center of G. Well, you know, here we have a relatively hyperbolic group, so the center is always finite, and so this will be a finite thing. Okay, so the important feature here is that there is another thing you need to describe the extension is that there is a morphism, natural morphism from F to out of G that's defined by, you know, choose a lift of the generators. This gives it normalized G, so it gives an automorphism of G, but it's only well defined up to inner automorphism of G. So we have this map here, and this map together with this element of H2 determines uniquely G prime up to isomorphism. And because in out of G there are only finitely many conjugacy classes of finite subgroups, there are only finite possibilities for this thing, and up to isomorphism, and that's how you get the corollaries. Okay. So let me now explain how we study those McCool groups. Okay. So recall McCool groups. So maybe I will start in the free group. So I'm given the free group and several subgroups of the free groups, and I want to understand all those automorphisms that act trivially on the HIs. So a McCool group, it's a subgroup of out of Fn. So it does act on outer space. Okay? So that's very nice. Outer space is a very nice contractible space. There is something that's not good if you want to prove something like finite presentation, is that the action is not compact. You have gone to a very maybe small subgroup of outer Fn, and so you have no co-compact action. And so the way we think about it is that given such a McCool group, we should replace the outer space by something else. And this is what deformation spaces are. So let's start with a group and its Gruszko decomposition. So Gruszko decomposition of a group is it's a splitting of the form G equals G1 star GS, and then there is a free group FR. What you should think when you see this picture, you should think of the picture below. this is essentially the same thing. This is a graph of groups decomposition, which is the same thing, except that you replaced the free group part with the rows. Okay, that's the more canonical object, because this free group here that appears in the statement is not canonical into conjugacy. I mean, only the G1, GS are well defined up to conjugacy. This FR is not, only its rank. And so this is a much intrinsic picture. Okay. And so related to that, there is the Gruszko deformation space. This Gruszko deformation space is a set of actions of G on simplicial trees, whose edge stabilizers are trivial, like here, and whose vertex stabilizers are exactly the conjugates of this guy. Okay, so this splitting is one point in the Gruszko deformation space, but you can deform it, in many ways. Like there's a big outer space here of Gruszko splittings, and maybe that's the replacement we want to look at for outer space. Except that here, if you do it for the free group, you will get just outer space. If you look, the Gruszko decomposition of the free group is just the rows, and the corresponding deformation space is, standard outer space. So you need to look at relative decomposition. Oops. So a relative Gruszko decomposition, it's a Gruszko decomposition, it's a maximal decomposition as a free product, where the relative part is the requirement is that those subgroup HI that you started with should be conjugate into the vertex groups GJs. Okay? And so you try to split, your free group as much as you can, keeping those HI in the factors. That's the meaning of this. Okay, and so now you can define the thing to understand the McCool group. The thing we need to work with is the relative Gruszko deformation space, so the deformation space of all those relative Gruszko splittings, and it's an easy fact that the McCool group you started with acts co-compactly now on this space. Okay. And a theorem, for this to be useful for what we want to do, is we want it to be contractible. And so that's still true. And so, because the action is co-compact, to prove, if you want to prove that this McCool group has the finiteness properties you want to prove, say, a finite index subgroup is a finite classifying space or finite presentation, say, then there almost remains to study stabilizers of trees in Gruszko. So the almost is a technical point that I think we missed in the first paper, which is about you have to be careful about the virtual problem. You have to be careful. So what I'm saying here is a little lie, but essentially you have your group acts co-compactly on some contractible space, and if you know finiteness properties of the stabilizers, and then you would get finiteness properties for your group, your McCool group that you want to study. Okay. So next step is so this is not next step, but it's something that when we thought about it, we thought, well, why only think about this deformation space for free products? And in fact, we realized that that what we proved for the contractibility of Gruszko deformation spaces did work in much greater generality. It did work for a general deformation space. So this is a very general definition. So you just take any group and acting on any simplicial tree, and then you can look at its deformation space. That's the set of all trees, T prime, simplicial trees, that have exactly the same elliptic subgroups. Okay. Then you may want to add some constraints on the edge group, like trivial edge groups as before. That's okay. This definition was introduced by Forrester, and he used it for two things. First, deformation space, for what he proved that two trees in the same deformation space, they are related by a finite sequence of moves. And so you can go from one to the other by these moves. And so, and the second thing is that when you look at GSJ decompositions of groups, so there are various definitions in different contexts. And what he proved is that all GSJ decompositions constructed by the authors all lie in a common deformation space. So they are related by those moves. Okay? And so, in fact, so the contractibility of deformation spaces that we had for free product.
Can you just say what the sentence number 2 means?
Yeah, sure, yes, okay. So well, I will go later about what is a GSJ decomposition, but it means if you know what this is, then you take one group and you take two GSJ decomposition of this group, okay? Say two cyclic GSJ decomposition. So maybe it's not so unique. And in fact, sometimes they are really far from unique, depending on the group. In hyperbolic groups, they are very unique. In general groups, they are not. And then the statement says that those two groups lie in the same deformation space, meaning that they have the same elliptic subgroups, and so that you can go from one to the other by a sequence of moves. Does this answer your question?
Two different JSJ decompositions, but I can still transform one into the other.
Exactly.
Using the same.
Using those moves. Okay. And in fact, so the fact that you can go from one to the other by moves is a connectedness theorem about the deformation space. Okay, you can go from one point to the other by moves. And in fact, what we can prove in great generality is that the space of the deformation space is indeed contractible. So I like to say that, okay, here the connectedness tells you that GSJ decompositions are unique up to sequence of moves, but the contractibility tells you that the sequence of moves is unique up to deformations of the sequence of moves. Yeah. Gilbert doesn't like this, but I think, okay, I like this way of saying it. So I mentioned GSJ decompositions, and so that's something that's important, very important, and introduced by Sela in group theory, coming from three-manifold theory. And so after Sela and Rip Sela, and many authors gave more general versions and with very nice construction with plenty of specific properties in each particular case. And what a kind of theorem, which is not a theorem, is that we proved with Gilbert, is that there is a good definition of what is a GSJ decomposition. I mean, one you can say, okay, and the second point is that the good object, I mean, the thing that is intrinsic, the thing that is canonical, is not a decomposition by itself in general. It's a full deformation space of splittings. And so here is a definition. Okay, so I told you that there exists a good definition. So maybe I can give it one. So I'm just saying for cyclic groups, but you can change cyclic to whatever essentially whatever class you want. So a cyclic decomposition of a group G is a JSG decomposition if it's a cyclic decomposition, so edge groups are cyclic, but you want them to be elliptic in any other cyclic splitting. So elliptic in the Basser tree of any other cyclic splitting. And then, so that's the first condition. Then you want to be maximal for this property. So maximality is in terms of, it means that, you know, you want the elliptic subgroups to be as small as possible. That's the maximality. You want to be the non-trivial, and the more non-trivial as possible, the most non-trivial as possible. I don't know how to say that. Le plus non-trivial possible. All right? Something that's important in all this is the fact that it's very often, it's very important technically, or to get rid of, not to look only at geometric decomposition of a group, but geometric decomposition of a group relative to a collection of subgroups. Okay, so this occurs in many contexts, and in the one I'm describing here. So here you would give the same definition, but you require additionally that all splittings are relative to the HI, meaning that they are elliptic in all the splittings considered. Okay, so it should be elliptic in the JH decomposition, but also the class of splittings you look at is only those splittings where the HI are elliptic. Okay, so that's about JH decomposition, and in some cases. So in many cases, so the important result is not the definition. The important result is that one can describe JSG decomposition, and the things where the vertices where things happen, the vertices that are you know, I mean that are not elliptic in all splittings. So that's where something happened, and they happen to be surface groups or related to surface groups depending on the context. And that's a very important fact in the theory. And another thing that happens related to hyperbolicity. But there's something missing here. There's missing that you need freely decomposable. So the JSG deformation space of a freely decomposable relatively hyperbolic group. Torsion-free relatively hyperbolic group contains canonical splitting. Canonical means you have this outer space, and in fact there is a fixed point for the full group that naturally acts there. Okay.
It contains, how many? Just one.
Well, yes, you can produce one, you know, center, one canonical point in this deformation. And so, so there are various ways of producing it. So Bowditch has very nice construction from the boundary of the hyperbolic group. We have a kind of algebraic one that works nicely too. Now, so remember we are trying to understand McCool groups. And so what we said is that there is this action of the McCool group on this outer space of Gruszko decomposition. And we said, okay, this space is contractible, the action is co-compact, so it's enough to understand stabilizers of points. And stabilizer of points is a stabilizer of a tree. And stabilizer of a tree it's a stabilizer of a splitting, and by the result of Levitt and Bas-Young that I first mentioned, it's expressed in terms of McCool groups. Okay, so to understand McCool groups, you have to understand McCool groups. But there's something that you did gain. See, is that you are reduced to studying McCool groups of freely decomposable groups. So here you can now use the JSG decomposition as described by Sela and others. So what does this description say? So it says that there are several kinds of vertices. So some of them where something happens, those are the surface groups. And they will give McCool groups that are mapping class groups. Okay? That's the example of McCool groups I gave just after the definition. And so here, those ones, you understand their finiteness properties. In fact, for instance, the finite presentation of these guys, I think it was first put by McCool, and that was the initial motivation for his study. Okay. Some vertex groups, those that don't split, where say nothing happens, then those groups will have finite McCool groups. Why is that? That's the reason is that is the Besse-Vinapolin argument. So Besse-Vinapolin argument tells you if you have, say, a hyperbolic group with whose automorphism group is infinite, then there will be an action on an R-tree. And then using Rip theory, you get a splitting. And so it means that, but the vertices I'm talking about here are those vertices that when there's no splitting that can occur. Okay, so because of this Besse-Vinapolin argument, those vertices where nothing happened, they have finite automorphism group. In fact, there is an additional case, an additional kind here that happens which occurs only in the relatively hyperbolic world. It's when some vertex groups of the GHD decomposition can be a parabolic group. Okay, so if this vertex group is exactly equal to a parabolic group, then something can happen, and what can happen is that you can get a McCool group of a parabolic group. Well, so now, what this means is if you want to understand, for instance, if you are if you are in a toral relatively hyperbolic group, so the parabolic groups here is just a Zn. Okay, what is a McCool group of some Zn? It's the set of matrices that are the identity on some subgroups. Okay, and matrices that are the identity on some subgroups in GLN, it's blocked upper triangular matrices. It's matrices of this kind. Okay. Maybe I know I want to be the identity somewhere. So where is it? Is that here? Yeah. Okay, that's. Is this correct? I hope so. And so this is the McCool group of an abelian group, and this is a very nice. Oops, would you do something? No. And so for instance, for instance, so this group here, this group of matrices is a finitely presented group. It has virtually it's an arithmetic group. It virtually has a finite classifying space, and so from this you can conclude the fact that all McCool groups of toral relatively hyperbolic groups, say, are finitely presented or have virtually a finite classifying space. Okay. What is it? Okay. So maybe so I have 10 minutes. Okay. Let me go back to this finite subgroup, the finiteness of conjugacy class of finite subgroups. So let me recall the statement. So you take a group that is hyperbolic relative to virtually polycyclic groups, and then there are only finitely many conjugacy class of finite subgroups. Okay. So this kind of statement is known for hyperbolic group and Cat0 groups, and the proof is very similar, and it goes as follows. So let consider, say, a Cat0 group. So it's a group that acts compactly geometrically and properly discontinuously and co-compactly on some cat-zero space. Take a finite subgroup. Well, the geometry of the cat-zero space tells you that any bounded subset has a unique center, so this finite group has to fix a point somewhere. Now, because the action is co-compact, you can conjugate this finite group so that its fixed point is somewhere in the compact set. And then, because the action is properly discontinuous, it gives you only finitely many possibilities up to conjugation for the finite group. Okay? The proof for the hyperbolic groups is essentially the same up to delta. Okay. And there are similar proof for mapping class group, Hennenfent, and arithmetic groups using, but you can't use directly the geometry or depending. So in this case, say to or you have to understand well the geometry to prove the fact that there is a fixed point on the nice space. So for instance, in a mapping class group, Kerckhoff proved that any finite group has a fixed point in Teichmüller space, and use this to prove this result for a mapping class group. For arithmetic groups, this is a theorem by Borel, and it follows from the fact that there is a nice fundamental domain for an arithmetic group. This is also known for nilpotent and virtually polycyclic groups, but here the proof is algebraic. I mean, as you can, I don't know, guess. And so for our proof, there are several parts. There is, in the same way, a geometric part when we have to prove that finite groups fix a point in the corresponding deformation space. Okay, this is something that Kohler did for Hennenfent and Zimmermann, and which extends naturally to our setting. And using that, the fact that the action is co-compact, we are reduced to understanding the finite subgroups in the stabilizer of a point once again, because here the action is not proper. Okay. So then we have to understand stabilizers of trees, and then there is a difficulty here because this property doesn't behave nicely. I mean, it doesn't behave nicely with finite index subgroups. Or I mean, you cannot go to a finite index subgroup, prove something for the finite index subgroups, and deduce the property. So this makes things complicated because, in all the results I mentioned for stabilizers of tree at the beginning, everywhere there was up to a finite index subgroup, you can prove you have this, and this. So we have to, we have to bother. We have to work and to avoid going to finite index subgroups. And so we have to describe point stabilizer. We have to replace McCool groups by slightly larger groups that allow us to not to go to finite index subgroups. And there is a final algebraic part. So at the very end, you reduce to McCool groups. These three kinds of McCool groups. So there are finite groups. That's okay. Mapping class groups. So it's known that they have this property, and then you have those McCool groups of parabolic groups. So it's known. It's known that the automorphism group of a virtually polycyclic group is an arithmetic group, but it's not known that McCool groups are. But still, well, it was known before the fact that. But still, we can prove that McCool groups of virtually polycyclic group have these properties. This is an algebraic proof that just generalized the fact that this property, in fact, was known for the full group of automorphism of a virtually polycyclic group, even before knowing that they were arithmetic. Okay. It's a difficult result to prove that those automorphism group of virtually polycyclic group are arithmetic, and we were not able to. We didn't try very much, but to prove that McCool groups of polycyclic group are arithmetic. maybe, yeah, I'm not going to start a proof of stabilizer for R3, so I will stop here.